Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. So last week in chapter 1 we started to review what you need to remember from statics for this class. So the key concept of the equilibrium of a body that is subjected to some external forces, how to calculate the reaction from the support, and how to access the load inside a body by using the method of sections. So now we are going to talk more specifically about some key conceptual concepts that are going to be useful to describe the mechanics of solids that are subjected to some loads. And there is really two key quantities that we will be talking over and over in this class. The first one that we are going to mention in this chapter is the stress. So the stress, which is what we are going to be defining in this class today, is what is going to tell us the risk of fracture. So if a given material is subjected to a stress that is high enough, then this material is going to break. So if we can calculate what is the stress acting within a member, then we can determine whether this member is going to break or not. And then the second thing, another key concept of CE 108, which is what we are going to talk about in chapter 3, is going to be the strain. So the strain, which we are going to talk about in the next chapter, is not going to tell us about the risk of fracture. It's going to tell us about the deformation of the member, like the geometrical deformation of the member. Is this member going to be elongated? Is this member going to be shrinked? Is this member going to be laterally deflected? So everything about the change in the shape or the change of volume of a member will be quantified by the strain. So those are really the two things that we will be talking about in this class. How much stress develops within a given member subjected to some loads? Is this material going to break or not? And how much strain is this material exhibiting? How much deflection, how much elongation is this material exhibiting? Like how much geometrical deformation? So far in chapter 1, what we saw is how to calculate the internal load within a member as a function of the external load. So we know, using the method of section, how to calculate the internal shear, the internal moment, and the internal axial load that is going to be applied within a member that is subjected to some external forces. But if you want to determine whether a given member is going to break or not, the load is not the quantity that matters. Why? Because in addition to the load, there is another factor that matters, which is the geometry of the member. The shape and the volume of the member will also determine its risk of fracture, not just simply the internal load. So when it comes to stress, why stress is the right quantity to determine whether a member is going to break or not, it's because it's combining the two effects of first the internal load that are acting within a given member, but also the geometry of the member. And those two things, the geometry of the member and the internal load that this member is subjected to, are key influential features that will determine whether this member is going to break or not. And stress is capturing those two effects at the same time. So when we talk about the geometry of a member, so we need to determine like what are the key aspects of the geometry of a member that determine its risk of fracture. So when we think about this, so for example, let's take the example of a member that is attached like this to a fixed support at the top, and then this member is subjected to an axial force F. So when you think about the geometry of this member, so you have its width, and then you have its length, and so the question is, which one of those two quantities, which one of those two geometrical quantities matters when it comes to determining whether this material is going to break or not? So when you think first about the length, so let's talk first about the effect of the length of this member. So if you take a given member like this, and then if you take a member that is twice as long, and let's assume that those two members are subjected to the same force F. So because they are attached to a fixed support on the top, and because this member has to be at equilibrium, we know that necessarily the fixed support is going to apply the same force F on the top, and this body as such is going to be at equilibrium. So now let's think about which one of those two member is the most likely to break first. And for this, we can calculate the internal load. And for this, we can use the method of section. So we can cut this member at a given position, an arbitrary position. Then we isolate, for example, the bottom, or we isolate the top. And we can use the method of section to say that if this member overall is at equilibrium, then each subsection of this member also has to be at equilibrium. So the bottom part also has to be at equilibrium. So then we can isolate the bottom part and apply the condition of equilibrium on this bottom part. And again, because this bottom part is at equilibrium, then the reaction force applied by the top to the bottom is going to be also equal to F, right? So in this case, since we are cutting this member this member in two parts, so now the top parts acts as a fixed support to the bottom part, so it's going to be applying a load to the bottom part. And in this case, if we say that the bottom part is at equilibrium, then this load must counterbalance the load that is applied at the bottom for this bottom part to be at equilibrium. So then what we can see here is that irrespectively of the length of this member, the internal load is always going to be equal to F. So the length of this member does not matter in this case. The length does not influence the risk of fracture. Why? Because the length of this member does not affect the value of the internal load. The value of the internal load remains the same, right? So the risk, the fact that this material is going to be on the right 2 times longer than the material on the left will not affect its risk of fracture. So this is not going to influence the risk of fracture. So now let's talk about the other geometrical features, which is the width. So the transversal width effect of the width. So again, let's take two examples of two beams. So one is the same beam as before, and another one is going to be the same beam, but this times 2 times thicker. And again, we are going to assume that those two beams are subjected to an actual load F. And due to the fact that those beams are at equilibrium, again, we know that they are subjected to the same force F at the top due to the fixed support for this beam to be at equilibrium. So same thing, we are going to use the method of section, cut this beam into 2 parts. We isolate the bottom, and we say that the bottom has to be at equilibrium. So this bottom is also going to be necessarily subjected to a force F. The force applied by the top to the bottom has to be equal to F for the bottom part to be at equilibrium. So now at this point, what we see is that the internal load does not depend on the geometry of the member, whether the member has a length that is different or whether the member has a width that is different. The internal load always remain the same. So now what about the risk of fracture? Here the key difference between the effect of the length and the effect of the width is that now if I look at the details of how this force that is applied by the top to the bottom is distributed throughout the member. So if we zoom in on this part, so if this is the bottom part. So I'm zooming in here on the bottom part, and I look at the intersection between the top and the bottom. So this is for the beam number 1 that is thinner, and now I'm going to do the same for the beam number 2 that is wider. So we know that the total force applied by the top to the bottom is equal to F. So that's the resultant force. So now if we look in more details about how the force that is applied by the top to the member, the top part of the member to the bottom part of the member is transmitted. So the reason because the top part applies a force on the member is because the top is attached to the member. So if you apply a force at the bottom will want to go down, but it's going to be prevented from going down because it is attached to the top. So the top is going to apply a force going up to prevent every point from the bottom from going down. So if you look at how this force is being transmitted, because the top is attached to the bottom, then it means that at every point of the interface between the top and the bottom, you have a small force that is applied by the top to the bottom. Same thing for the beam that is wider here. At every point of the interface between the top and the bottom part, then there is a small force that is applied by the top to the bottom. At every point of the beam at every point of this interface is attached. The top is attached to the bottom, so there has to be a small force that prevents those two beams from being disconnected from each other. So now if we look at those small force dF that are applied at each point of the bottom part. So we know necessarily that all those forces, when you sum them up, they are becoming equal to F, where F is the resultant force. So F is going to be the sum of all the small forces over the surface. So if you take this surface here, which is the cross section of the member, you take the sum of all the small forces along this surface, that gives you the total resultant force that is applied by the top to the bottom. So now we know that this total resultant force is the same on the left and on the right. Again, when we use the method of section, we can see that the internal load does not depend on the length, or doesn't depend on the width of this member. So this total resultant force is the same on the left and on the right. So if the total force F is the same on the left and on the right, what does it mean for the small forces dF that is applied at each point of the interface between the top and the bottom? So here, if we assume, to simplify, but this is a good assumption, that the small force dF that is applied at each point of the top of the interface between the top and the bottom is the same irrespectively of the position within this interface. So if we think that over this interface here, the force is homogeneously distributed throughout this interface, which means that at each point of this interface, the force applied by the top to the bottom is the same. Then, in this case, since the surface over which the force is transmitted by the top to the bottom is not the same between the left and the right, since the total resultant force is the same, and since the sum of the small forces over the entire surface is the same and equal to F, then since the surface is larger on the right, then necessarily the small force that is applied at each point of the surface will be smaller on the right? So you take the sum of all those small forces, and you know that the sum of all those small forces is going to be the same on the left and on the right because it's equal to F. So since you are summing those small forces over a larger surface on the right, then necessarily, since you are summing over a larger surface, despite the fact that the total sum remains the same and remains equal to F, then it means that the quantity that you are summing, those small forces delta F, will be smaller on the right. So the F in this case will be smaller on the right. Another way of understanding this is that we have the same total force F that is applied by the top to the bottom on the beam on the left and on the beam on the right. But in the right, this total force F is going to be distributed throughout a larger surface. So at each point of the surface of contact between the top and the bottom, the small localized force is going to be smaller because this total force F is distributed over a larger surface. So it means that in this case, because the same load is distributed over a larger surface on the right, the member on the right is less likely to break than the member on the left. Why? Because again, so the member on the right is less likely to break. For the same force, it's less likely to break. Why? Because for the same force, this force is distributed over a larger area. So what this is telling us is that in the case of stress and in the case of estimating the risk of fracture of a member that is subjected to a given load, what matters is the load. The load itself matters. Of course, if there is no load, then there is no risk of fracture, so you need a given load. But then the second thing that matters is the area of the surface over which the load is applied. If a given load is applied on the small surface, then this load is going to be very intense and it's going to be distributed over a very small surface, so that at each point of the surface you have a very high intensity of this load. On the other hand, if this load is applied to a larger surface, then at each point of this surface, the intensity of the load becomes smaller, and there is going to be, in this case, a lower risk of fracture. So when it comes to estimating the risk of fracture of a member, the load matter, but also the geometry of the member matter, but not any geometrical features. The length, the longitudinal length of the member does not matter. That's what we saw here, but the width matters. The surface over which the load is transmitted matters, and that's what the stress is going to be capturing. It's going to be capturing the load and also capturing the effect of the surface over which the load is applied. So now let's see a more formal definition of stress. So let's assume that you have a given body. So this is a given body. This body is going to be subjected to some external forces. And then if we want to calculate the probability for this body to fracture, then we need to be able to calculate this, the concentration of load, the intensity of the load at each point of the body, and this is what is going to be the stress. So for this, what we are going to do is to isolate a small cube within this body. So we are going to isolate within this body an infinitely small cube, and the size of this cube will be infinitely small, so we are going to write its dimension dl, where dl is a very small quantity. And now we are going to isolate this small cube and see what are the forces that are applied to this cube. So let's assume that we have a given space like this, where this is the axis x, axis y, and then the axis z is coming towards you. And now let's see what we get if we zoom in on this small cube and see what are the forces that are applied to this cube. So what we are going to do for this is to redraw the cube. So let me draw this cube. So this is the cube along the x and y direction, and then this is the width of the cube along the z direction. So now let's see what are the dimensions of this cube. So this cube has the dimension delta L along the 3 dimension. So whether it's on the z, x, and y direction, this dimension is the same. And so we are going to define the surface of each of the side of this cube. So the surface dA is simply dl to the square. So dl times dl is the surface of each side of this cube. So let's define the point O that is at the center of this cube. So now let's see what are the potential forces that can be applied to this cube along each of its surfaces. So along each of along each of the 6 surfaces of this cube, you can potentially have some forces. So here we will be focusing on the 2-dimensional case where we assume that there is no force along the z direction. So we will be simply focusing on the x and y direction. So this is going to be a very general assumption within 108. In many cases, problems can be defined simply in 2 dimensions. So many of the problem, most of the problem that we will see in CE 108 will be in 2 dimensions. So we are going to assume that there is, in this case, no force, no shear force, no normal force that is applied along the z direction. So applied along the surface that is orthogonal to the z direction. So all the forces for now will be applied either along x or along y. So now let's see, what are all the possible forces that can be applied? So first, you can have a force that is applied on the right. So you can have a normal force that is applied on the right. So that's going to be a small force because it's applied on a small cube. So we are going to write this force with a d. It's going to be called dn, d, because it's going to be a very small force applied on this very small cube. And because this is a normal force, we are going to call it n. And because it's applied along the direction of the x-axis, we are going to call it dnx. So now we know that this force, necessarily for this body to be at equilibrium, this force must be balanced on the other side by exactly the same force, dnx, for this body, for this small cube within the body, due to the method of section. Since this entire body is at equilibrium, each small cube within this body also has to be at equilibrium, and hence if you have a force applied on the right, necessarily you need the same force but opposite direction applied on the left. So then you will also have a normal force potentially that is applied on the top. This is going to be a normal force. It's normal, orthogonal to the surface, so it's also a force that we can write n. It's a small force, so it's dn, and it's along the y-axis, so we call it dny. Same thing, if you have the force applied on the top, then necessarily for this small cube to be at equilibrium, you need the same force that is applied at the bottom. So now those are not the only possible forces that can be applied, right? Because you can also have some shear force, some force that will tend not to elongate, not to compress, but to shear, to deform, to change the shape of those materials. So the first type of force that you can have is a shear force that is going to be applied on the right, and that is going to be pointing up. So this is the force that is also going to be a small force because it's applied on a small surface. We're going to write it V because it's a shear force, not a normal force. So this force is applied along the surface, not orthogonal to the surface. And in this case, we are going to define the direction of this force using two indexes. First, we are going to say that this force is applied on the x surface. And then we are going to say that this force is along the y direction. So this is how we are going to refer to shear forces. The first index here tells you on which surface this force is applied. And here in this case, this is the surface that is orthogonal to the x-axis. So we call it the x surface. And then the second index, y, here tells you the direction of the force itself. Here the force is pointing up. The force is going along the y-axis. So we call this force dvxy. dvxy, where the first x is the direction of the surface and y is the direction of the force. So then, same thing, similarly, if you have this shear force applied on the right, then necessarily for this body to be at equilibrium, you need the opposite shear force applied on the left, where again, this is going to be exactly the same shear force dvxy, but going down this time because this body has to be at equilibrium. And then the last type of force that you can have is a shear force that this time is going to be applied on the y surface. So this shear force is also a shear force, so we call it V. This time this shear force is applied on the y surface. It's applied on the surface that is orthogonal to the y-axis. And this time this force is along the x direction. So this force, we can write it dvyx. And similarly, because this force is applied at the bottom, for this body to be at equilibrium, you need the opposite force applied at the bottom that is going to counterbalance. So this is going to be the same force, dvyx, which is going to be ensuring that this body is at equilibrium. So now let's see if all those forces are independent from each other, or if there is some relationship between those forces. So one way that we can figure this out is by looking at the equation of equilibrium for this body. So we know that this small cube has to be at equilibrium. So we can write the condition of equilibrium, the equation of equilibrium for this small cube, to see if there is any relationship between those small forces. So let's see what we get. So first we can use the fact that the sum of the force along the x direction is equal to 0. So the sum of the projection of the forces along the x-axis has to be equal to 0. So what do we get if we do this? What are all the forces that are along the x-axis? So first we have the Dnx force that is applied on the right. It's towards the positive x, so its projection is positive. Then you have this other force Dnx that is applied on the left, and this one is towards the negative x, so it's having a negative projection. What else do we have? We also have two shear force that are along the x-axis, so they also need to be included. We have dvyx that is on the top. This one is pointing towards the positive x, so it has a positive projection. And then there's the one at the bottom that is pointing towards the negative x, so it has a negative projection. And we know that the sum of those forces has to be equal to 0. So in this case, we don't learn anything new, because we already knew that dnx minus dnx plus dvyx minus dvyx is equal to 0. So there is nothing, this equation doesn't teach us anything new. Let's see what we get by saying that the sum of the forces along y equal to 0. So same thing, now we look at the projection of all the forces along y. So we have the two forces dny that are at the top, positive projection, and at the bottom, negative projection, and we have the two shear forces applied on the right and on the left. The one on the right is going upward, so it has a positive projection, that's dvxy, and you have the one on the left that is going downwards, and we know that the sum of those projections has to be equal to 0. Again, here we do not learn anything new because we knew already that dny minus dny plus xy minus dvxy is equal to 0. So now let's see if we learn anything from the moment. So let's write the fact that the sum of the moment about the point O at the middle is equal to 0. So let's see what are all the forces that will be creating a moment about O. So let's look at all the forces. So first we have the Dnx forces. So those normal force Dnx, they do not create any moment about O. Why? Because their line of action is going through the point O. So their moment would be 0 about O. Same thing, dny, their line of action is going through the point O. So the normal force dny also do not create any moment about the point O. So the only forces that will be creating a moment about O will be the shear forces. So let's see what we can get from that. So first we have the shear force that is applied on the right. So dvxy. So the force that is applied on the right, the shear force dvxy, is going to create a positive moment about O. It's creating a force that is going to tend to make the body rotate anti-clockwise, so it's a positive moment. So that's going to be a positive projection. The moment is equal to dvxy, that's the intensity of the force, and we need to multiply this by the arm of the force, and here the arm of the force is dl divided by 2. So that's the contribution of the moment coming from the shear force on the right. Then let's write the moment coming from the shear force on the left. So same thing, this dvxy, the shear force on the left that is going downwards, is also going to create a positive moment that tends to make the body rotate anti-clockwise about the point O. So it's going to be a positive projection. The moment is going to be dvxy, the intensity of the force, times the arm of the force, dl over 2. So now let's see the moment that are created by the shear force applied by the top and the bottom. This times those two shear force tend to make the body rotate clockwise. So those are going to be negative moments, moments that have a negative projection. So let's see, the moment created by the shear force on the top is going to be negative. The shear force is dvyx, the arm of the force is also dl over 2. And same thing for the shear force at the bottom. It also has a negative projection. The shear force is dvyx times the arm of the force, dl over 2. The sum of all of those moments is equal to 0. So now if we look at what we learn from this, so we can see that we can simplify everything by dl. And if we simplify this expression, what we have is 2 times dvxy divided by 2, so we get dvxy, and we get 2 times dvyx divided by 2, so we get minus dvyx, and this thing is going to be equal to 0, which means that in this case dvxy has to be equal to dvyx for this body to be at equilibrium. So in this case, this is an important relationship because it's telling us that in 2 dimensions, for a body that is at equilibrium, there is only one type of possible shear force. The shear force that is applied on the horizontally on the top or the bottom surface has to be equal to the shear force that is applied vertically on the right and on the left surface. So there is only one type of shear force in 2 dimensions, only one type of shear force. Why? Because again, the shear force that is applied on the x surface along the y direction has to be equal to the shear force that is applied on the y surface along the x direction. This is a condition that has to be true for this body to be at equilibrium. So since there is only one type of shear force in 2 dimensions, then there has to be also only one type of shear stress. So again, this is not the case for the normal forces. For the normal forces, you have the force along x, you have the force along y, and those two forces do not have to be equal to each other. So you have two types of normal forces in 2 dimensions, but only one type of shear force in 2 dimensions. So it means that if we want to define the state of stress in 2 dimensions, which is what we are going to do now, there will be two normal forces and hence two normal stress, one along x, one along y, and only one type of shear stress. Y again, because the shear stress along x has to be the same as the shear stress along y. So based on this, we can define the general state of stress in 2 dimensions. And the way we are going to define this is by following what we said at the very beginning of this lecture, is that what matters to define the risk of fracture is the force and how it is applied, how this force is distributed over the surface. So what matters is the ratio of the force per unit of surface. If the surface is very small, then this force is going to be applied to a small surface, and in that sense you will have a high stress, you will have a higher risk of fracture. And if this force is very large, then if the surface is very large, then the force is going to be distributed over a large surface, and in that case the stress will be lower, the risk of fracture will also be lower. So for the definition that we will be using for the stress, so let's start first with the normal stress. We are going to define the stress, and that's a definition. We are going to define the stress along x as the ratio of this small force that is applied along x divided by the area over which it is applied. So here we have a definition that is a little bit arbitrary because it depends on how small we define this small cube. So as a reminder, this was the initial body, the initial potato that we considered, and then we took a small cube within this body to define the stress at this along this cube. But here, this small cube is an infinitely small cube. This was just a mathematical object that we used to define the stress along a given point O. And we don't want the definition to depend on the size dl that we chose for this small cube. Like, the definition should be independent on this size. So we want this cube, we need to have a cube. We cannot simply define a point, because you cannot have a force that is applied exactly on a given point. That's what we talked about in the first lecture, like those concentrated force, they can never be applied exactly on a given point. Like, to apply a force necessarily needs to be applied to a surface. So we need to define a small cube to calculate the forces. We cannot simply define a point. But ultimately, we want this cube to be as small as possible so that it's as close as possible to a point. So if we want to do this, what we will do, mathematically speaking, is that rather than defining the stress as simply the load divided by the area, we are going to say that we are going to take the limit of this ratio when the surface becomes very small. So we're going to take the limit of this ratio as the cube becoming infinitely small and infinitely close to zero. So that way, if we take the limit towards this cube becoming infinitely small, then the definition does not depend on the size of the cube anymore. So that's a mathematical definition that allows us to robustly define the stress. In practice, when solving problem, we never use this formal definition. We never have to calculate limits or anything like this, but robustly speaking, the proper way to define the stress is to take the limit over an infinitely small surface to make sure that this surface become as close as possible to a single point. So this is the definition of the normal stress along y. It's the force along the y-axis divided by dA, where dA is the surface over which the load is applied. And again, this is what the stress is capturing. It's combining the effect of the load and divided by the surface over which it is applied, because the surface over which the load is applied is also an important geometrical feature that dictates whether this material is going to break or not. So then we can define also the other types of normal stress. We said that there would be two types of normal stress: sigma x, this is along x, and then sigma y, that is along y. And same thing, sigma y is going to be the ratio of the normal force along y divided by the surface over which this force is applied. And same thing, we are going to take the limit where dA becoming very small. So that's going to be the mathematical definition of the normal stress. We can also define a shear stress. So again, same thing for the shear stress. So we're going to write this one tau. So this one was sigma, and this one is tau. And so for the shear stress, same thing. We are going to say that this is the ratio of the shear force. So remember that the shear force, this is also the same. dvxy is equal to dvyx, and we take the ratio of this shear force over the surface over which it is applied, dA, and we take the limit when dA tend to go towards 0. So this gives us the shear stress tau. That again is the ratio of the shear force divided by the area over which it is applied. In terms, so like one way to represent this, to summarize this, is that if you have a small 2D system like this, and if you define along a given point a very small square like this, so you will have 3 types of stress that matters. If I'm asking you to calculate the state of stress at a given point, you need to calculate the value of sigma x, so that's the normal stress. You need to calculate the value of the stress sigma y, the normal stress along the y-axis, and you need to calculate the value of tau, where tau, here is only one shear stress, independently of whether it is applied on the x or on the y-axis. So 2 things that we need to talk about. First, the unit of the normal stress. This is the same as the unit of the shear stress tau, and because it is a ratio of a load in Newton divided by an area in a square meter, the unit of stress is going to be in Newton per square meter. So this is also the same as a Pascal. All the potential unit for the stress are PSI, so the American units, which I'm not really going to use in this lecture. We are going to stick to international system unit, but 1 PSI would be 6895 Pascal if you want to convert one into the other. And then you have 1 KSI, which is 10 to the power 3 PSI. So that's when it comes to the units. And then the last thing that we are going to talk about regarding the stress, which again is going to be something important for this class, is going to be about the sign. Every time we define a quantity in this class, we need to agree on what is the sign convention that we will be using for this quantity. What does it mean for this quantity to be positive? What does it mean for this quantity to be negative? So we need to define again what are going to be a positive stress, what is going to be a negative stress. And this is a convention, right? So there is no specific reason to define one stress being positive or one stress being negative, but we need to agree on what are the conventions so that we can speak the same language. So let's see the convention for the three types of stress: sigma x, sigma y, and tau. So, and then we are going to see what is the positive convention and the negative convention for each of those shear stress and normal stress. So when it comes to the normal stress, the first thing to remember is that we are always going to define a positive stress if it's a tensile stress, a stress that is pointing towards the outside, a stress that tends to elongate the system. So when it comes to sigma x, a positive normal stress is going to be something like this, that tends to, where the stress points towards the outside. That's a stress that tends to elongate the material. And on the other hand, we are going to define a negative normal stress if it's a stress that tends to compress. If it tends to compress the material, then that's going to be a negative normal stress by convention. So this one is the positive convention. This one is the negative convention. Same thing for sigma y. We are going to use the same definition, that if the stress is pointing towards the outside, then that's going to be a positive sigma y, and if the stress is pointing towards the inside, then that is going to be a negative sigma y. So that's going to be the negative convention for sigma y. And finally, the last thing is for the shear stress. So when it comes to the normal stress, in this case, the sign of the stress really makes a difference, because a positive normal stress tends to elongate material, the volume is increasing. A negative normal stress tends to compress material, their length is decreasing, their volume is decreasing. So in this case, a positive and a negative normal stress really has a different physical meaning. In the case of shear stress, a positive or negative shear stress really doesn't have any different meaning. It's just about whether the body is going to be deformed clockwise or anti-clockwise. There is really no reason that one should be positive or one should be negative, because it's exactly the same meaning to shear something clockwise or anti-clockwise, which is not the same for the normal stress. It's physically different to elongate and to compress a material. So for the shear stress, a positive or negative shear stress is exactly the same thing. You have the same chance to break a material by shearing it positively or shearing it negatively, which is not the same again for a normal stress. It's different to take a material and elongate it or compress it. Usually it's much easier to break a material by elongating it than by compressing it. So in this case, again, for normal stress, a positive versus a negative normal stress, this really has a different physical meaning. But for the shear stress, the sign doesn't have a clear physical meaning. But still, we need to agree on the sign so that we can make sure we have the same convention and we speak the same language. We can compare our result meaningfully. So by convention, we will be defining a positive shear if it's a shear force that is applied like this, in the same way that we defined the shear force in the previous slide, or if it's a shear force that is like this. And we know in this case that because of the condition of equilibrium, that's what we calculated 2 slides ago, those two shear force has to be the same. So that's what we are going to be using for the positive sign convention for the shear stress. That's going to be a positive shear stress. And then a negative shear stress. So we are going to define it as follows. So either a shear stress like this or a shear stress like this. That is going to be a negative shear stress. So that's going to be, in this case, the positive convention. Is this going to be the negative convention? So one thing that is typically a little bit hard for people to comprehend is that, is this really the same thing? It doesn't look at first sight that those two positive stress are the same thing, because one seems to be deforming the material clockwise and one seems to be deforming the material anti-clockwise. So it looks at first sight that those two stress should not be the same thing. But if you look a little bit in more detail at the effect of those two stresses, so let me represent again those two systems in the case of the positive sign convention. So if I look at the material here on the left, so again we are going to define the positive shear stress. What is going to be the effect of this shear stress? This shear stress is going to deform the material like this. So then let's look now at the other one, this one. So same thing, I'm going to represent this body again, and I'm going to apply the positive shear stress. What is going to be the effect of this shear stress? It's going to deform the material like this. So now, are those two deformations the same or not? One way to look at whether those deformations are indeed the same or not is to, let's look at let's define 4 points, A, B, C, D, A, B, C, D. So this is the four corners of this square. So now to compare those two deformations, let's look at the distance between A and C and the distance between D and B. So if we look at this deformation here, the effect of the deformation is that now the distance between A and C becomes smaller after the deformation that it was before the deformation. And same thing now, if we look at this case here, the distance between A and C also becomes smaller after the deformation than before the deformation. Another way of saying this is that if you take this body here after the deformation and you just slightly rotate it like this, then it becomes exactly the same as this body. Or again, a last way to see this is that if you take this angle here, it's the same as this angle here, and this angle here is the same as this angle here. So the deformation here between this stress and this stress is actually exactly the same, and that is why those are two definitions of the same positive shear stress. And now just to make sure that indeed this deformation is not the same, so now if we look at what would happen to this material after it is deformed, it would look like this. If we define the same A, B, C, D points, now the distance between A and C now becomes larger after the deformation, which was not the case in the case of this deformation. And if we look at this angle here, like the angle ABC, now this angle becomes larger than 90 degrees, although it was smaller than 90 degrees in the case of a positive shear stress. So this is why in this case, those two deformations are indeed the same, and they are different from the deformation that are associated with the negative shear stress. So again, the things to remember, the most important is to just remember the positive sign convention for the normal stress Those are the stress that tends to elongate the material, where the stress is pointing towards the outside. And then in this case, in the case of the shear stress, this is the positive convention. Going up if the stress is applied on the right, going down if the stress is applied on the left, going right if the stress is applied at the bottom, or going going right if the stress is applied at the top, or going left if the stress is applied at the bottom. This is the positive sign convention that we will be using for the shear stress.